Dear students, in the previous class, we have seen different methods of ionization procedures in mass spectrometry, and these ionization procedures can result in different types of fragmentation patterns. And we are going to explore different various kinds of fragmentation patterns and what kind of fragmented molecular units could form out of these ionization techniques. And we are mainly going to focus on the electron impact ionization. And as you know that we hit the molecule with a very high energy electron beam, which has got an energy around 70 electron volt, which is almost 6 to 7 times greater than the energy required for breaking carbon-carbon single bond. So as a result of this interaction, not only does the molecule uh, forms a radical cation, the formed radical cation will have or will possess a lot of energy, which is more than sufficient to break the bonds apart in the radical cation. And this fragmentation of the radical cation or the molecular radical cation could result in different types of fragmented molecular units, such as neutral radical, a radical cation, or a radical cation, and so forth. Okay, so say for example, if methanol is being hit with an electron beam, so the electron in the electron beam can knock out an electron from methanol molecule, and it's easier to remove the electron from a lone pair electron of oxygen, which is lesser tightly bound to the atom compared to the electrons involved in chemical bond, the sigma bonds here. So the electron will be one electron will be taken away by this electron, so that it forms two electrons, so that you will have a radical positive character on the oxygen atom of the hydroxyl functional groups here. So you will get a methanol radical cation. We call this one as a molecular ion, okay, because essentially it has got the same molecular formula as the parent molecule, but uh, rather it has one lesser electron with it. Okay, this radical cation, since it possesses a lot of energy, it could form either cation, okay, CH2OH plus, by removing a hydrogen from the species, a hydrogen radical from the species, or it could form a methyl cation, CH3 plus an hydroxyl radical. Okay, so there are a lot of possibilities like this. So there are, how do you know what kind of fragments form, or what are the possible ways in which fragments can form? There are some general conventions which have been empirically formulated from the observations of different fragmentation patterns resulted by the impact ionization on different molecules. And the one of the first conventions is that when you consider a molecule of this form, such as cyclohexadiene, uh, then if you subject this molecule to an electron beam, it will knock out one electron from the one of the pi electrons, because pi electrons are easier to kicked out from the molecule, compared to sigma electrons, which are tightly bound. And so one of the pi electrons in one of these pi bonds can be ejected out of the molecule, and which will result in a radical cation nature. So here, if we represent the molecule by its Lewis structure, okay, then it is always better to localize the cationic charge on one of the carbons involved in the pi bond formation, and the radical character on the other carbon. For example, compared to structure A, it is always preferable to write the radical cation as either structure B or structure C. Okay, in structure B, the radical, if the electron is being ejected from this pi bond here, then the radical could be either shown as being localized on this carbon and the cation on the second carbon, or the other way around, cation on the first carbon and the radical on the second carbon. So it's always good to represent the structure of the molecular cation in such a way that the radical and cation are separately shown on different carbons, okay, rather than this structure. It's always better to represent the radical cation as either B or C. Okay, so this is the first convention where you need to localize the cation and the radical on different atoms. But this convention is not always possible to obey in the case of alkanes, simple alkanes. Okay, so when the molecule is subjected to ionization by electron impact ionization, as we said, it's always easy to remove an electron from a pi bond rather than from a sigma bond or from a heteroatom lone pair, because it's loosely bound electron pair compared to the electrons involved in sigma bond formation. And there could be two different kinds of bond breaking mechanisms. One could be following a homolytic bond cleavage, and the other mechanism could be involving a heterolytic bond cleavage. Okay, so homolytic bond cleavage usually happens by the shifting, or the removal of one electron from the bond to one of the constituent atoms that forms the bond. Okay, but in heterolytic bond cleavage, two bonding electrons will be shifted towards one of the atoms that forms the bond. Okay, so for example, in the first example, if you subject the molecule to electron impact ionization, oxygen has got the the oxygen atom has got the lone pair, so one of the electrons in the lone pair will be taken away by the electron beam, making a radical positive character on the oxygen. Then this species could undergo homolytic cleavage, in the sense this bond here, one of the sigma bond electrons can shift towards this direction, and the other sigma bond electron can shift towards the CS3, forming a CS3 radical. And while these electrons shifts towards the CS2 oxygen bond, this electron of the radical cation species will shift towards this bond, forming a double bond here, leaving a positive character on the oxygen. And this is a homolytic bond cleavage, okay, where we represent the one electron shift by a half-headed arrow. Okay, and whereas in heterolytic cleavage, where we represent the bond cleavage by the shifting of electrons using a completely headed arrow, where an example is shown here. Okay, so here it's easier to remove the electron from the halogen atom, lone pair electron from the halogen atom, and the radical cation is being found on the bromine when the molecule is hit with an electron beam. Then this bromine radical cation take away the complete to the sigma bond electron density towards it. Okay, so the two electrons that will be shifted towards bromine will neutralize the positive character here, making this one a bromine radical and this one as a cation. Okay, so this one is a heterolytic cleavage mechanism. Okay, so the type of fragment that forms out of a fragmentation process depends upon whether the molecule undergoes a homolytic or heterolytic cleavage mechanism. So the general rule of thumb are that the most of the fragments that are formed by electron impact ionization are even electron cations. Okay, cations generally do have even electrons. So, we usually represent this one by M plus. So these cations, since they possess higher energy, they are most likely to split into more numbered even electron cations. Okay, and the probability of breaking a bond, okay, depends upon its bond strength. The lesser the bond strength, the easier is to break the bond. Okay, and the stability of the fragments formed. Okay, if the formed fragments are stable compared to the parent molecule, then it's highly likely that the parent molecule will be broken apart or fragment apart to form a stable from a number of stable fragments. Okay, and in addition, the cations that are formed as a result of electron impact ionization, they rather rearrange or decay into more stable cations. So this is another convention. And for a molecule that contains a ring system, you need to keep in mind that at least two sigma bonds must be broken for getting the ring to fragment. Okay, if the ring needs to get fragmented into two separate species, at least two sigma bonds should be broken in the ring system. Okay. Okay, so these are just general conventions, but there are some empirical general rules okay, that have been formulated by observing the fragmentation patterns of different molecules, which are being given in the next slides. Okay, so before going into the general rules, let us see what is a base peak and a molecular ion peak. And this mass spectrum, where we have shown the relative abundance of the fragments that are being formed by electronic bit ionization of cyclohexane, and this relative abundance of the fragments are being plotted versus the mass to charge ratio of each of the fragments. Okay, so and for cyclohexane, the molecular weight of the molecule is 84.096, and exactly at the same value we get a peak. Okay, so this peak is due to the molecular ion peak, where we have knocked out one electron from the cyclohexane to form C6H12 dot plus radical cation of cyclohexane. Okay, so the molecular ion peak is nothing but the molecule minus one electron. So this peak gives us some information about the formula as well as the structure of the molecule under investigation. Okay, and the most intense peak, or the fragment with the highest relative abundance, gives the most intense peak, and this peak is called the base peak in the mass spectrum. Okay, sometimes the molecular ion peak could be the base peak. Okay, sometimes base peak could be different from the molecular ion peak. It depends upon which fragment that gives the highest relative abundance. Keeping the concept of molecular ion peak and the base peak, if you represent the molecular ion peak by m dot plus or simply m plus, then the first convention or the rule or the guideline says that the relative intensity of this m plus peak would be the greatest for straight chain molecule compared to branched chain molecules, and the intensity of the m plus peak would be decreasing as the branching ratio increases. Okay, so as the molecule gets more and more branched, the intensity of the molecular ion peak will get decreased. Okay, and the relative height of the second rule says that in a homologous series, say for example for alkanes, the relative height of the molecular ion peak will decrease as the chain length increases along a homologous series. For example, if you take the case of a propane and hexane, then the relative height of the molecular ion peak of hexane would be lesser compared to the molecular ion peak in the intensity of molecular ion peak of propane. Okay, and the third rule says that the bond cleavage will be favored at alkyl substituted carbons. Okay, and with the probability of cleavage increasing as the substitution increases. As the carbons are getting more and more alkyl substituted, there is a more and more probability, or there is more chance for the bonds to get broken at that typical carbon. Okay, so this is in accordance with the Stephenson's rule, because which says that compared to primary carbon, the secondary carbon is more stable. Okay, and compared to the secondary carbon, the tertiary carbon is more stable, and the allylic carbon is more stable than tertiary carbon, and benzylic carbon is much more stable than allylic carbon. Okay, so this basically stems from the fact that the carbocations and the radicals that form out of the cleavage of the carbons in these molecules will also follow the same trend in stability. Okay, where the benzylic carbocations are more stable than allylic carbocations, which is more stable than tertiary carbocations, and similarly the benzylic radicals are stable than allylic radicals, which is more stable than tertiary radicals that forms on tertiary carbons. Okay, so this Stephenson's rule must always be followed, and again another simple rule is that if a bond breaking happens in a molecule, okay, the bond could get broken into molecules of or fragments of equal size, some which is very impossible almost all the time, but rather the molecule will get broken into a larger fragment and a smaller fragment. Okay, so in that case the larger fragment will take up the radical character when it gets fragmented away, whereas smaller fragment will take the cationic character. Okay, so when the molecular radical cation gets broken, the larger fragment will take the radical character of the molecular radical cation, whereas the smaller fragment will take the cationic character of the molecular radical cation. And again, if the molecule has got, or molecular radical cation has got some double bonds or cyclic structures or aromatic rings in the system, then these structures will stabilize the molecular ion, okay, and then the molecular ion will be difficult to get broken, and therefore the intensity of the peak corresponding to the molecular ion will be much more prominent or much more increased in the mass spectrum. Okay, so again, if the molecule has got a double bond, such as the one in cycloalkene, such as in cyclohexene, then the molecule will preferably follow a allylic type cleavage, forming an allyl carbocation. Okay, so for example, if this cyclohexene is subjected to electron impact ionization, then one of the pi bonds will be removed from this part, which forms a cationic character on one of the carbons and a radical character on the second carbon. Okay, and this system will undergo homolytic cleavage at the allylic bond here. Okay, so this electron will come here, and this bond will be broken, so that this electron shifts towards this direction, forming a double bond here, and this electron will move to this carbon to form a radical here. Okay, so you will get an allylic type radical cation. Okay, and this species, which has got a positive character here, a double bond here, and radical here, can undergo resonance with this structure, where when this double bond pi electron density shifts towards this carbon, okay, this carbon will be left out with a positive character or cationic character. For saturated rings such as cyclohexanes, which bear side chains, then when they are subjected to radical ionization or electron impact ionization, it will form a radical cation. Then the bond could get broken here, right here. In that case, the cyclohexane saturated ring will take up the positive character on this carbon, and the smaller substituent will take, or side chain will take away the radical character. In the case of unsaturated rings such as cyclohexane, which we have shown in the previous rule, where it could undergo allylic type cleavage, it could also happen to this ring that a retro type Diels-Alder reaction can happen to the molecular radical cation, so that it could form a radical cation and a neutral alkene species. Okay, so what happens here is that when this cyclohexane is being hit with an electron beam, the electron beam could take away one of the pi electron from this bond, leaving a positive character on this carbon and a radical character, or and an electron on this carbon. Okay, so here homolytic T cleavage can happen to this bond, and this sigma bond. Okay, so what could happen is that this bond, this electron and this bonding electron can combine to form a double bond here. Okay, and this electron and this electron can come here to form an alkene here, and then this electron will be moved towards this direction to form a radical cationic species here. Okay, and in the case of aromatic compounds, especially those which bear a alkyl type substituent, okay, it could usually form benzylic cations upon which is being shown here, upon electron impact ionization, and this benzylic cation can undergo instant rearrangement to form a propylium type cation, which is being shown here. Okay, here is the mechanism. When this is hit with a electron beam of high energy, one of the pi electron can be lost, forming a radical type cationic character here. Then this bond can undergo homolytic type cleavage, leaving a radical character on this R functional group, and then a pi bond density right here. Okay, so once this pi electron density shifts towards this carbon sigma bond, it forms a double bond here, forming a benzylic cation, which then undergoes rearrangement to form tropylium cation. And this tropylium cation usually appears as an intense peak at a embase ratio at 91. So if you see moderately or high intensity peak at an intense embase ratio of 91 for an aromatic compound, it's highly likely that that is due to a tropyline cation, which indicates that we have got an alkyl substituted phenyl ring in the molecule. Okay, for molecules that contain heteroatoms, the carbon-carbon bond that is adjacent to the heteroatom will get preferably broken or fragmented, okay, through a homolytic cleavage mechanism, okay, likewise shown here, where the radical cationic character is localized on the heteroatom here, and this electron can shift towards this direction, and this bonding electrons can shift towards this direction, forming carbon oxygen double bond and leaving a positive charge on carbon, positive charge on oxygen, and then it could form a linear alkane chain with a propyl radical character, okay, and this can undergo rearrangement to form a typical cationic species here, okay. And if the fragmentation process or cleavage process results in the formation of small stable molecules like water, carbon dioxide, ammonia, H2S, etc., then cleavage is most or fragmentation is most often flavored in that typical reaction pathway, okay. So that means when the molecule gets subjected to electron impact ionization, the fragmentation pattern will always follow a pathway in which the fragmentation forms stable fragments or stable neutral molecules. So in addition to this very predictable fragmentation patterns, there could be some intramolecular rearrangement processes as well, okay. Say for example, one of them is called McLafferty rearrangement, and we will deal with this McLafferty rearrangement in more detail at the end of this mass spectrometry course. And just take a note here that McLafferty rearrangement happens to molecule with a carbonyl system in which it can adopt a structure or geometry in such a way that the gamma hydrogen, okay, this is alpha carbon to carbonyl carbon, beta carbon, and gamma carbon. There is a gamma hydrogen which can orient in such a way so that it forms almost a cyclic hexagonal structure, okay. Then in that case, this oxygen can take up this hydrogen, gamma hydrogen, forming OH dot plus, and in that process we get a double bond here, right here, and this bond will be broken, forming a neutral alkene species here, okay. So this one is a very predictable McLafferty type rearrangement which is being usually observed in carbonyl compounds, okay. And in addition to this very predictable or absolute rearrangement mechanisms, there could sometimes you could see, or it could also happen that you could see some very random, okay, very barely understood rearrangement mechanisms, which are often considered as random rearrangements, such as the one shown below, okay, right here. Okay, so here is the concept of molecular ion peak in much more detail. Here you have been shown the mass spectrum of benzamide, and when this is being subjected to an electron impact ionization, it's highly likely that it could take up the heteroatom electron, most probably on oxygen, forming a radical ion species here, molecular radical ion, and this molecular ion species will show up at an M-Base value of 121, okay. So this peak is due to the molecular ion M plus dot, or simply we show it as M plus, and this molecule can undergo fragmentation in two pathways, okay. One in which just only the NS2 group is being lost, okay. So this bond gets broken, and the NS2 will take away the one of this two bonding electron densities, okay. These two sigma bonds will go away with NS2, leaving a radical character on NS2, and the carbonyl carbon will be left with a positive character. So this one is a carbocation, and which will appear at an M-Base value of 105, okay, right here. And it could also happen that the bond gets broken here between carbon and the carbonyl carbon, phenyl carbon and carbonyl carbon, and then as a result what could happen is a phenyl radical will be lost, leaving a C double bond or NS2 plus cation, Okay, so this cationic species will be almost exclusively localized on carbonyl carbon here. Okay, and this will show up at an embased ratio of 44, which is a small peak compared to the peak at 105. Okay, so this one is a preferred fragmentation pathway over this pathway, and this one can undergo further fragmentation by removing a neutral species such as carbon monoxide. So this species will be getting lost by acquiring the sigma electron density of this bond, leaving a positive charge on this carbon here, which is a phenyl cation, which usually appears at an embased value of 77. So this one is due to the phenyl cation. Okay, so the peaks due to all the subsequent fragments, if they are possible, will show up in the mass spectrum, and the relative intensity of these peaks will depend upon the stability of the molecular cation, then molecular cation, and the stability of the formed fragments. Okay, and this and the some other factors such as reaction thermodynamics and kinetic favorability. So the molecular ion gives us a lot of information about molecular mass and elemental composition, and it also decides what kind of fragments are formed, and because the fragments are being formed from the molecular ion species, so the fragments must be consistent with the properties of the molecular ion peak. And what happens is, as we hit with the electronic bitter ionization, as we hit the molecule with the electron beam with a lot of energy, this energy could actually break apart the molecular ionic species. So if the molecular ionic species is instantaneously gets broken just after formation, then you will not see a lot of intense peak for the molecular ion species. So rather, you may not even see the molecular ion species at all. Okay, if the molecular ion species is very unstable and gets fragmented instantaneously into subsequent fragments or parent fragments, or daughter fragments. And so sometimes you may not see the molecular ion peak in that case. So in that case, in order to get information about the molecular ion species, we use instead of hard ionization techniques such as electron imbibed ionization, we use soft ionization techniques such as chemical ionization. But in chemical ionization, it could also happen that the formed fragments may interact with the sodium plus 2 form adducts, which could interfere with the fragmentation peaks. And the molecular ion species is the one for which the embased ratio is the peak that contains the most abundant isotope of all the elements involved. That is a convention. Okay, the embased ratio of the molecular ion peak is the one that contains the most abundant isotope of all the elements involved. Okay, so the requirements are that the molecular ion peak or the molecular ion should be the one with the highest mass. Okay, which is called the isotopic caveat, and it must be an odd electron ion for electron imbibed ionization, because in electron imbibed ionization, one electron is being removed from the molecule to form a radical cation, so it should be an odd electron ion. Okay, and it should be able to yield the most important ions in the high mass region by loss of logical neutral species such as water, H2S, carbon monoxide, etc. Okay, so if these three conditions fails, then the formed species cannot be molecular ion species. But even if the fragment that is being formed passes all these tests, it may also happen that it may not be the molecular ion peak. So as we said, the abundance of the molecular ion peak or the intensity of the molecular ion peak depends upon the stability of the molecular ion. Okay, and the energy that is input to form the molecular ion species. If it is too much, the molecular ion species will not be stable. And again, there is a obviously clear correlation between the properties and structure of the molecule with the magnitude of the intensity of the molecular ion peak. Okay, the abundance of the molecular ion peak depends actually on factors such as the molecular structure, and depends on the intensity of the molecular ion peak increases with the unsaturation and the rings in the molecular system, because as we have more unsaturation index or have more rings in the system, it will be difficult to break or fragment the molecules into further smaller fragments. Okay, so the greater the stability, the more will be the intensity of the molecular ion peak. Okay, and the intensity of the molecular ion peak decreases with the chain branching, as we have seen earlier. And as of now, the effect of molecular weight is not actually clear, because people have not been able to find a direct correlationship between the intensity of molecular ion peak and the molecular weight of the sample. Okay, and if you supply a lesser energy to ionize the molecules, such as the one we do in soft ionization techniques, then the formed molecular ions will have very low energy, and we call this as cool ions. And then the formed molecular ionic species will be more stable, and therefore it will be there will be lesser chance of this one to get fragmented further. So the intensity of molecular ion peak will be higher in that case. But whereas in hard ionization techniques such as electron impact ionization, the formed molecular ion species will have a lot of internal energy. Then it can be called as hot ion, and it will immediately or instantaneously fragment into smaller fragments, and the intensity of molecular ion species or peak will be lesser in that case. Okay, and the ease of ionization increases down on a column in the periodic table or to the left in an arrow. Examples are alcohols versus mercaptans, or alcohols versus amines. So this one is a chart which shows the stability of molecular ionic species as we go down from the down to the top in the upward direction. The lifetime of the molecular ionic species increases. That means as we go down from here to all the way up here, the formed molecular ionic species will be more stable. Okay, so say for example alcohols, the molecular ionic species of alcohols will instantaneously get fragmented, and the branched hydrocarbons have got a little bit more lifetime for molecular ionic species. And as we go up, we can see that in this order, the most stable compounds are the one that contains conjugate double bonds or a degree of unsaturation, and aromatic, those that contain aromatic rings. Okay, so because they are very difficult to fragment, because they are more stable species. And while fragmentation, we could get species with the odd electron ions or with the even electron ions. And usually, as we have seen in electron impact ionization, as the beam encounters the molecule, it will knock off one electron from the molecule, and then the molecule will be left with an unpaired electron, left with one electron, and then it will form a radical cation. Okay, so that means in order for making a radical cation, the molecule should also already have an unpaired electron density. Okay, or pi electron density for that matter. For example, in this ether, okay, when it encounters the electron beam, one of the electron can be removed, most probably from the oxygen lone pair, forming a radical cationic nature here. Or one of the other rarest case is that one of the sigma bond electrons can be kicked off. Okay, so this is a rare possibility, making a radical ROR dot plus. Okay, in the case of ethylene, the pi electron density can be easily removed from compared to the sigma electron density. So one of the pi electron can be kicked out from this one, forming a ethylenic radical cation. Okay, and in the case of methane, okay, all the four sigma bonds are similar, so one of the sigma bond can lose one electron, forming a radical cationic nature, forming a methyl radical cation. And these radical cations could further undergo fragmentation to more stable even electrons ions such as cations. Okay, for example, here the methyl cation undergoes fragmentation to form a methyl radical cation, undergoes fragmentation to form a methyl cation and a hydrogen radical. Okay, sometimes it could also happen that the molecular radical species CH4 dot plus, okay, that is present already in the system, could abstract this hydrogen radical to form an MH plus species. Okay, that means in the case of CH4, it could form CH plus species, and this one will show up at exactly 1 unit MBZ value greater than the MBZ value of the radical cation. And this one is more stable than the radical cation. cationic species, and this will not undergo much of fragmentation, resulting in lower fragmentation uh, uh, you know pattern. And how do you see whether the fragmentation results in a an even electron ion or an odd electron ion? Okay, so this ring plus double bond rule, which is almost the same as the hydrogen deficiency index rule, is useful in seeing whether the formed radical species or the radical cationic species is an even electron or odd electron species. Okay, suppose if the formed fragment can be analyzed to find its molecular formula, okay, or empirical formula for that matter, then say for example if it is of the formula C6Hy NZ, then the ring plus double bond rule says that x or the hydrogen deficiency index is equal to x minus half y plus 1/2 z plus 1. Okay, so if the resultant value here is a half integer, then the found species is an even electron species. But if this value is an integer value, then the formed species is an odd electron species. For example, if you take the case of C5H5N plus, which is a fragment that could result as a result of fragmentation from a parent molecule, then here x is 5, y is 5, and z is 1. Okay, then you can get 5 minus 5/2 plus 1/2 plus 1. Okay, so here you have got 5/2 is 2.5 and 1/2 is 0.5. 2.5 plus 0.5 is 3, plus you have got a 5 here. 5 minus 3 is 2. 2 plus 1, 3. Okay, so it's an integer value. Then this molecular ion species is an odd electron molecular ion. Okay, but in the case of a C7H5O plus, okay, then the number of oxygen atoms are not being counted in the formula. Then we get a x is 7, y is 5, z is 0. Okay, so 5/2 is 2.5. 7 minus 2.5 is 4.5. 4.5 plus 1 is 5.5, which is an integer plus 5 plus 0.5. Okay, then this fragment is actually an even electron species. In the case of H3O plus, okay, x is 0, z is 0, but y is 3. Okay, 3/2 is 1.5, minus 1.5 plus 1 is 0.5. Okay, so it's an even integer species. Okay, so there are some other rules as well which are quite helpful in deciding the fragmentation pattern or predicting what kind of fragments that would form. Okay, for most of the elements that could be present in organic compounds, there is usually a relationship between the mass of the element as well as mass of the most abundant isotope of the element as well as its valency. Okay, for example, odd mass elements will have a valency of odd value, whereas even mass elements usually have a valency of even value. Okay, hydrogen has got an odd mass and odd valency. Carbon has got even mass and even valency. Oxygen has got even mass and even valency, and so on. Okay, so even mass, even valency, odd mass, odd valency. Okay, so there is this typical correlation, except for nitrogen. Okay, nitrogen has got a mass of 14, which is an even value, but a valency of 3, which is an odd value. Okay, so there is some exceptional rule for nitrogen here. Nitrogen rule says that if a compound contains no or even number of nitrogen atoms, the molecular ionic species that is formed from this typical compound will have an even mass number. So this is nitrogen rule number 2. Okay, say for example, if you could take the case of you can see yourself about these molecules which does not contain any nitrogen, but for molecules such as ammonia, NH3, then nominal mass is 17. Okay, because it contains one nitrogen atom here, then the nominal mass should be odd value. Okay, but none of these molecules contain hydrogen, so the number of hydrogens is 0. So all these molecules are at even mass number. Okay, whereas pyridine contains one nitrogen, and the normal mass of this compound would be at an odd value. Okay, so this is what this rule, nitrogen rule 2 says. Okay, and the nitrogen rule 3 applies to all ions, and it says that for if the compound contains an even number of nitrogen atoms, okay, if the compound contains an even number of nitrogen atoms, and if there is an odd electron ion that is being formed from this compound, then it will have an even mass number. Okay, so this is rule number 1. But if the compound contains an odd number of even number of nitrogen atoms, okay, same as above, and if the compound forms an even electronic species, even electron ionic species, then this species will have an odd mass number. Okay, I hope you understand this thing. Okay, we have a compound which contains an even number of nitrogen atoms. Okay, we have a compound which contains an even number of nitrogen atoms, and if this compound forms an odd electron ionic species, then its mass will be having an even value. Okay, but if the same compound has got an even or forms an even electron ionic species, then the mass of this species will have an odd mass number. Okay, so this is what the rule says. Okay, which is being summarized in this table. Okay, and the reverse is not always true. Okay, so this one is corollary to the nitrogen rule. Okay, so if the molecular ionic species, which is m dot plus, if it is an odd electron ionic species, okay, once it undergoes fragmentation, it can undergo fragmentation in two ways. This odd electronic molecular ionic species can split into form an even electron cation and a radical, or it can get split into an odd electron radical cation and a neutral species, neutral atom, or neutral molecule, or neutral fragment. Okay, but if the molecular ionic species is an even electron cation, then it could get split into an even electron cationic species plus a neutral fragment. And an unlikely scenario or a rare scenario is that it could also get fragmented into an odd electron radical cationic species plus a radical of which is represented by R dot here.